Hello students, this is Professor Chalai, and in this video we're going to look at precipitation reactions and solubility rules. By the end of this video, you should be able to predict whether precipitates will form from certain reactions, and as always, you can follow along with our Chapter 4 workbook. Now, you might be wondering, what is a precipitation reaction and what is a precipitate? Well, a precipitation reaction is simply a reaction in which dissolved substances react to form one or more solid products. So here's where you mix two solutions together, or more than two solutions sometimes, and out of those solutions you will see a solid product. That solid product is called a precipitate. Now, you might be wondering, well, how do we know when certain products are going to be precipitates or not? And to figure that out, we need to memorize what we're calling the solubility rules. Because ionic compounds, as we know, are made up of a cation. Let's look at NaCl, for example, a cation and an anion. But NaCl will dissolve in solution, in aqueous solutions. So NaCl will always dissolve. But there's some ionic compounds, some salts, for example, that will not dissolve. And instead of being aqueous, they'll be solid. They will precipitate out of the solution because they're not soluble in water. And to figure out which salts will be soluble and which salts will be insoluble, we will look at the solubility rules. And here's how we read this table. In the blue are going to be compounds that are always soluble, and in the red are going to be exceptions to those. So for example, if our salt has anything from group 1A, such as lithium ions, sodium, or potassium ions, they're going to be always soluble no matter what anion they're paired with. So here, for example, we looked at NaCl, which is aqueous, but if it was Na2CO3, sodium carbonate, it will also be aqueous. It doesn't matter what the anion is, as long as it has sodium, lithium, potassium, anything from group 1A, it'll be soluble. Let's look at another example. Let's look at sulfates. So here it says sulfates are going to be soluble with some exceptions. So for example, if we had, picking one at random, if we had iron 2 sulfate, it's going to be soluble. However, if we have one of these exceptions with sulfate, let's say barium sulfate, it's going to be not soluble, it's going to be insoluble, as an example. In the bottom part of the table, we have stuff that are always going to be insoluble with some exceptions. For example, let's look at sulfides. Sulfides are always going to be insoluble, right? So if we had, let's say, iron 2 sulfide, FeS, it's going to be insoluble, so solid, except if we have any one of these exceptions. So one of the exceptions is group 1A stuff, so we know that anything with sodium is going to be soluble, so aqueous, so that's an exception. Or calcium, barium, and strontium. So if we have, let's say, calcium sulfide, that's also an exception, it's going to be soluble. So this is how we read this table. There's a little mnemonic in the bottom here to help remember which ones are going to be soluble and which ones are going to be insoluble. You should memorize this table and know all of these rules. Okay, let's use these rules to predict whether things are going to be soluble or insoluble. Let's look at number 9. Nickel sulfide. Well, is nickel sulfide going to be soluble or insoluble? Let's look at the table. The table says that sulfides are always going to be insoluble, and nickel is not one of the exceptions. So this is going to be insoluble. I'm just going to do one more. Magnesium phosphate. Let's look at our table. Phosphates are always going to be insoluble. Magnesium is not one of the exception, so this is also going to be insoluble. Try to do C and D on your own and let me know how you fare. But use the table to try to figure out whether these are going to be soluble or insoluble salts. Okay, let's look at number 10. Number 10 says to predict the result of the mixing of these concentrated solutions. And if a precipitation is expected, write the balanced net ionic equation for the reaction. So net ionic equation. So here we have potassium sulfate and barium nitrate. I would write these out in formula form. So potassium is K plus, sulfate is SO4 2 minus. So the formula would be K2SO4. They told us that it's a soluble solution. Let's try the other one, barium nitrate. Barium is in group 2A, so barium has a charge of 2 plus. Nitrate, if you've memorized, has a charge of 1 minus. So barium nitrate will have a formula Ba1 NO3 2 to balance the charges, and that's aqueous. All right, when we mix these together, we're just going to exchange the ions, the cations and the anions. So let's use the potassium cation with the NO3 minus, the nitrate anion. That will give us KNO3, right? Plus 1 charge minus 1 charge. So we don't need to worry about the charges there. And then Ba2 plus with the SO4 2 minus, so BaSO4. They have a 2 plus and a 2 minus charge, so they're already balanced. Okay, now we need to figure out whether there's going to be any precipitates formed. Well, we know from our table, this has potassium, which is always soluble, and it has also nitrates, which are always soluble. So this is going to be aqueous as well, always soluble. Barium sulfate, let's look at our table. Sulfates, we talked about, are always soluble, but barium is one of the exceptions, so that means it's going to be insoluble. So this is going to be solid. So as the question asks, a precipitate is expected, so we need to write the balanced net ionic equation. Okay, so before we do the balanced net ionic equation, let's balance this equation first. So we have K2, but only one K on the right-hand side, so let's make that a 2. That gives us 2 NO3s. There are already 2 NO3s over here. There's one barium, one sulfate, so everything's balanced. Okay, to write the net ionic equations, we're only going to look at, remember, for the net ionic equations, everything that's aqueous usually breaks apart and they stay the same on the left and the right. So the only thing that's changed in this is the barium sulfate. So the net ionic equation is just going to be the formation of this barium sulfate. So we're going to have barium 2 plus aqueous plus sulfate, SO4 2 minus aqueous, going to give us our barium sulfate solid, net ionic. But for those of you who were not sure how I got that, let's break this up into the complete ionic first and then the net ionic. So potassium sulfate, we have 2K plus aqueous plus SO4 2 minus aqueous. Okay. Barium nitrate aqueous breaks up into barium 2 plus aqueous plus 2 nitrate aqueous. That's on the left-hand side. On the right-hand side, we have 2 potassium nitrates aqueous, which breaks up into 2 potassium aqueous and 2 nitrates aqueous, plus barium sulfate, which is solid, so that doesn't break apart. Barium sulfate solid. What stays the same and what changes? 2 potassium on the left, 2 potassium on the right, so that cancels out. 2 nitrates on the left, 2 nitrates on the right, cancels out. The sulfate and the barium are aqueous on the left, but it's together in a solid on the right, so they don't cancel out. And so that's how we end up with this net ionic equation right here. Okay, try B and C on your own and let me know how it goes. Okay, let's look at number 11. We have a solution with barium 2 plus in it in an aqueous solution. It's in a water sample. We have other chemicals such as sodium chloride, sodium hydroxide, or sodium sulfate available. Which one would we add to our barium solution to get a precipitate, and what is the formula for that precipitate? Well, let's look at barium. So remember, we have sodium chloride, sodium hydroxide, and sodium sulfate available. So these are all solutions we can add to our barium solution. So let's figure out what barium we're going to be soluble with. So here we are. We have a chloride, a hydroxide, and a sulfate. So let's look at those. Chlorides are part of the halogen group, and they're always soluble, but barium is not one of the exception. So if we add chloride to the barium, it will not form a precipitate, so we can't use chlorides. Let's look at hydroxide. Okay. Hydroxides are always insoluble, but barium is an exception, which means if we add it to the barium, it will not form a precipitate, so it can't be hydroxide. Let's look at sulfates. Typically, our sulfates are going to be soluble, but look at it. Barium is an exception. So it means that if we add barium to sulfate, we will get a precipitate. So we will add sodium sulfate to our barium solution. What is the formula for the precipitate? Well, it will be the barium 2 plus the sulfate 2 minus ions combined. They're both aqueous. This has a +2 charge, that has a -2 charge, so we just need one of each to balance them out, which means we'll end up with BaSO4 solid. All right, try number 12, and then I'll go over a couple of them as an example. Okay, let's look at this compound right here. We have silver nitrate plus sodium chloride. Let's mix the ions. So silver nitrate comes from 2 ions, Ag plus and NO3 minus. Sodium chloride has Na plus and Cl minus. So if we mix the ions, we'll get the silver with the chloride, so AgCl, and we'll get the sodium with the nitrate, so NaNO3. We need to look at our table to figure out which one's going to be soluble and which one's going to be insoluble. We know that all sodium and all nitrates are soluble, so this is always going to be aqueous. If we look at our table, we'll find that silver chloride is actually solid. So this is going to be our precipitate, and that's the formula. So AgCl, because the charges are just 1 and 1. Try the others by yourself. Let me know what you get. But just for the sake of argument, we're going to look at this one, sodium chlorate. So sodium will break apart into Na plus, the chlorate ion is ClO3 minus, and then we also have barium 2 plus and CO3 2 minus. So those are all the ions floating around. If we mix them up, we'll get sodium carbonate, so Na2CO3, right? 2 sodiums to balance the 2 minus charges. And we'll have barium chlorate, so BaClO3, but barium has a 2 plus charge, chlorate only has a 1 minus charge, so we may need to double the chlorate to balance the charges. If we look at our table, all sodium things are going to be soluble, so this is always aqueous. Barium chlorate, let's look at that now. Here we go. Chlorates are always going to be soluble. There's no exceptions. So it doesn't matter what it's paired with, chlorates are always going to be soluble. So in this one, that's aqueous. None of these are insoluble. There are no precipitates for B. All right, let me know how you go on with the others. And if you have questions, as always, please let me know. And finally, let's look at number 13. You can go ahead and do them answer all of these, but I'm just going to do part A for you for number 13. All right, so each of these, we're going to write a balanced molecular equation, a balanced complete ionic equation, and a balanced net ionic equation. So let's start with our molecular equation. Okay, we're starting with sodium sulfide and silver nitrate. If we look at our our solubility rules, we'll find that this is aqueous because, again, sodium always soluble, and this is also aqueous, nitrate always soluble. All right, before we can write the products, let's figure out what ions these come from. So sodium is Na plus, sulfide is S2 minus. Here we have silver is Ag plus, and nitrate is NO3 minus. So let's exchange the ions. The positive from this one and the negative from this one will give us sodium nitrate. And if you wondering, it's all aqueous because sodiums are soluble and nitrates are always soluble. And then let's do the other one. the cation from the silver and the anion from the sulfide. We need to double the silver to balance the charges, so we have Ag2S. All right, let's figure out whether Ag2S is soluble. We go up to our table. Sulfides are insoluble. Silver is not one of the exceptions, so that will be a solid. So, solid. Now we need to balance this molecular equation. We figured out the products, now we need to balance it. Okay, we have 2 sodiums on the left, 1 sodium on the right, so let's make that a 2. That gives us 2 nitrates on the right, but only 1 nitrate on the left, so let's make that a 2. That gives us 2 silvers on the left, there's 2 silvers on the right, so that's all okay. We have 1 sulfide on the right, 1 sulfide on the left, so we're now balanced. All right, let's look at our complete ionic equation now. Remember, complete ionic equation, we just break apart everything that's aqueous. So we have 2 sodium plus aqueous plus an S2 minus aqueous. For here we have 2 silver plus aqueous plus 2 nitrates minus aqueous. On the right hand side we have 2 sodiums aqueous plus 2 nitrates aqueous plus this compound is a solid, so we don't break it apart. It's Ag2S, silver sulfide, solid. All right, now let's figure out our net ionic equation. All right, everything that stays the same, we cancel out. So 2 sodiums, 2 sodiums, 2 nitrates, 2 nitrates, everything else remain the same. So our net ionic equation would be 2 silver plus aqueous plus a sulfide aqueous going to give us silver sulfide solid. All right, try those with B, C, and D and let me know how that goes. If you have questions, please message me. Otherwise, I'll see you in the next video when we talk about acid-base reactions. See you then.